Okay, yeah. Um, so we introduced yesterday. So yeah, yesterday we introduced the standard enthalpy of formation, and we said that this is the change in enthalpy that accompanies the formation of one more of a compound. Okay, so this is the change in enthalpy that accompanies the formation of one more of a compound from its elements with all substances in their standard state. So basically what this means is you are trying to form something, and then everything, so you are looking at the formation of one more of a substance, right? So meaning the beauty with focusing on one more or on an individual more, like I had said last time, is the fact that you can easily be able to play around, multiply, divide that based on the number of moles that you have at that particular point. But if only you only have a value, then that wouldn't do you good, right? But when we know what the standard enthalpy of formation for something is, and we know that the number of moles have increased, we can be able to manipulate and be able to play around them in that particular way, isn't it? So that's the key thing that's important for us to take note of. Okay, so yesterday we talked about what those standard conditions are. So basically, what we are talking about, we are looking at conditions which can be replicated by everyone, right? So let's say if they say the standard enthalpy of formation for something is this, it should be something that can be replicated. Remember that those times when we are talking about when we are talking about the what's this the accuracy, the precision, that topic, right? We talked about the importance of having things that can be what things that can be replicated, because that's one way in which we know that whatever that we are doing is reliable. And the best part of it, that it does not matter whether you are doing an experiment from America or from anywhere else, the values are what are going to be the same, so long as things are maintained under standard conditions. So you're talking at or rather looking at something that's a reference state, right? So maybe the temperature is going to be this, the pressure is going to be that, things that everyone can be able to replicate. So that's something to take note of, right? And so we say that for a gas, the standard pressure would say is 1 bar, okay, or you can say 1 atmosphere, okay. So you would say that. So that's something that's important to take note of. Okay, then conventional definition of standard state. So for a compound, the standard state of a gaseous substance is a pressure of exactly 1 atmosphere. So that's something that everyone can replicate, isn't it? Whether you are in Tanzania, you are wherever you are, you can at least be able to have a gas with that atmosphere, right? Okay, or rather with that pressure. Yeah, let's put it that way. Then for a pure substance in a condensed state, liquid or solid, the standard state is the pure liquid or solid. So basically what you're looking at, if the normal state of a substance is a solid, then its standard state is what is when it's solid. Like for instance, water, we know that the standard state for water is what is liquid, right? So we know that when you have something that's a gas or vapor, that's not pretty much standard, right? Anyway, but that's just to give you an idea. I'm not saying that that's not standard, but I just want you to have an idea of that. Or like the way we know that like that carbon dioxide is gas and then you find it in solid, that is not standard, right? Exactly. So then for a substance that is present in solution, remember for this one the concentration has to be 1 molarity. You may remember when we were calculating the standard cell potentials, we were using standardized 1 molarity, isn't it? So that's important. That's something that we want to take note of, right? Okay, then now we can now talk for an element. So the standard state of an element is the form in which the element exists under conditions of 1 atmosphere and 25 degrees Celsius, right? So basically what you're talking about, if we, for instance, we talk about oxygen, at a pressure of 1 atmosphere, we are going to have oxygen, right? And at that temperature of 25 degrees Celsius, it's going to be gas. Then for sodium, you expect it to be solid, right? And then for mercury, the standard state is going to be liquid. Huh? So you may be wondering, why am I stressing this? This is very, very important, because you may remember yesterday that I mentioned that you can't cancel, even if you've got water in gaseous state and water in liquid state, you can't cancel the two. Remember those things that we were doing yesterday, right? You can't cancel the two. And the reason why you can't do that, it's because these are, what can I put it? So these are substances, or these are, we can say, yeah, so these are substances that are in different states, right? So you can't just play around them like that. So now we are now going to look at how we can make use of what we've discussed to be able to solve a number of questions, of course. And remember, we are still looking at Hess's law, and so that's our main subtopic, right? So several important characteristics of the definition of enthalpy of formation will become clearer as we consider the formation of nitrogen dioxide from the elements in their standard state. So remember, uh, there is something that I mentioned yesterday to say this is the topic where you find things such as half nitrogen. And the reason why we are doing that is because we want to obey the definition of enthalpy of formation. So, for instance, looking at the first equation, right, we've got half nitrogen gas uh, plus gaseous oxygen is equals to nitrogen dioxide, right? And we've got that standard enthalpy of formation. Now, notice that we've got half nitrogen too, which is something that we were not seeing, or we've not been seeing in the past topics. So why do we do this for this? It's because, remember, the standard enthalpy, you are looking at one more of product being formed. But we know that if we try to balance this thing by using, let's say, there we put two, then for again for oxygen, then we add another two, then we are going to have to, oh, sorry, let's say if we added two to the product, yeah, because for us to balance that equation, we have to add the two to the product, but that will be what? That will be two moles of nitric dioxide. That will no longer be the what? The standard enthalpy change of formation, because remember, by definition, the elements have to be in their standard states, which we know nitrogen is supposed to be gaseous under standard conditions, and oxygen has to be gaseous under standard conditions, right? And then it has to be what? Produce one more of product. So again, that's something that's very, very important. So enthalpies of formation are always given per mole of product, with the product in its standard state. Okay, so that point, has everyone gotten it? So the reason why I'm stressing this is because when we come to apply Hess's law, these are some of the things that we have to be looking at. Then let's now look at the formation reaction for methanol. So methanol, this is a type of an alcohol, right? So you've got methanol, ethanol, propanol, things like that, right? Okay, great. So what else do we have? What else do we have? Yeah, so the standard state of carbon, we know it's graphite, right? So graphite is the normal standard state. When you have diamond, and you can even just think of it, right? Diamond, we don't find diamonds anywhere and everywhere. So that should give us a hint to say diamond, it's not really, really the standard form, because if it were the standard form, then most of carbon would have been in diamond form, right? Okay, hope that adds up. Huh? Yeah, so there we see then the standard states for oxygen, hydrogen, and the atomic gases. So now to balance the oxygen, you see we've put a half oxygen there, so that we leave the product to being a one more. So that's just what they are trying to explain there. Now, let's now look at a question. So we are going to deal with this the same way that we dealt with what we were doing yesterday, where we explain through the what is being calculated. Then after we understand the concept, then we try out an example. Okay. without using without using what they are looking at, so that even as you be going through the notes on your own, you'll be able to understand with the guidance that we are going to be giving one another, right? So that's how we are going to go about it. That's fine, right? Okay, so now now, okay, so I think I'm just going a little bit ahead of myself. Let's just wait a bit. Okay, so now, so the so the standard enthalpy, so the standard enthalpy of formation for some common substances, so those are given in table 6.2. You can see that table on the upper left. Okay, so the importance of the tabulated standard enthalpy of formation values is that enthalpies for many reactions can be calculated using these numbers. So you remember yesterday how we were given four equations, and from those four equations we were able to formulate more or less, we were able to formulate and actually be able to find the enthalpy of formation of a particular substance just based on those four equations which were given, right? So that's something that we could do there. So that's something that you'd want to. So that's something that you'd want to know, right? So to see how we can use all these things and be able to find the standard enthalpy change for the combustion of methane. So combustion of methane, you are basically getting methane and then burning it in excess what? In excess oxygen. So you are going to have the carbon dioxide and water being formed, right? Okay, so you see that all those are in their standard state, right? Now, for this reaction, it becomes very difficult to calculate the standard enthalpy change, mainly because, it can be very difficult to account for the heat that's going to be lost and all those things. So usually these are things that we use, or the enthalpy of formation, they are very important, especially in those reactions where it can be difficult to directly calculate the what? Calculate the enthalpy changes, right? And so that's where Hess's law comes in. But now we are going to take more or less a long cut, and then this long cut that we are going to take, it's going to actually help us understand Hess's law in depth. That makes sense, right? So that's how we are going to go about it. So enthalpy is a state function, so we can invoke, so remember state function where it does not matter the path which you use, right? You can make one step, you can make two steps, but so long as you are moving from point A to the same point, to the final point, your enthalpy is going to be the same, right? So you're going to use that Hess's law, and then you're going to make and then you're going to choose any convenient pathway from reactants to products, and then we know that when we reverse uh, a certain equation like we were doing yesterday, we change the what? We change the value. And when we multiply through an equation, because enthalpy is an extensive property, yeah, so we are also going to multiply that enthalpy. I know I've talked a lot. So, in case someone has got a question, kindly ask so that we can be able to proceed together. Okay, okay, great. So, I'm glad to hear that everyone is comfortable. So, now before we can look at the notes, I want us to dwell on this picture here, right? So, this is just going to help you appreciate these things, right? So what's happening in this reaction? So we know the reaction that we are talking about, it's the combustion of what? Of methane. Okay, oh yeah, of methane in excess oxygen to form carbon dioxide and water. Now you see what they're doing is they're getting the reactants. So they've gotten the reactant, so I'm sure you've seen that reactant methane, and you've seen that reactant oxygen, right? Now oxygen is okay, like there's nothing that we can do on oxygen because it's just the same thing, right? But but for methane, it's a compound, so what we do is when we look at our products, carbon dioxide and hydrogen, we know that the carbon dioxide is coming from from the carbon part of methane, and the water is coming from the hydrogens which are in methane. So therefore, what we do is we break what we break this methane. Okay, so here we are going to be using the standard enthalpy what of formation. Okay, so we break the what? So we break that methane into its elements. Now, okay, let me just allow somebody that wants to join. Just allow someone that wants to join. Okay, let's just allow some. I think there's someone that wants to join. Okay, I don't know why, but I'm having challenges. Uh, mm, Going back there. Anyway, so okay, let me see if I can. Yeah, so that's what we are having, right? So now this is very very important because now you see we are breaking the methane into its constituents, right? But we know that if you are breaking this methane into its constituents, what does it tell us? Okay, what does it tell us about the standard enthalpy of formation? It's basically you go reversing the standard enthalpy of formation, isn't it? I hope everyone has gotten that point, right? So because you are breaking this methane into its constituent elements, it's the same as the reverse of the standard enthalpy of formation for methane. Because we know that for us to form methane, it was carbon and hydrogen which combined to form methane, right? So that's that. So there we know one reaction that we are going to use. I hope this makes sense, right? Then for oxygen, remember that for an element in its standard state, there is no energy that is required to keep something in its standard state. For instance, you see that oxygen, it's in a gaseous state. You don't have to use any heat for that oxygen to be in that state, right? So the enthalpy change for an element in its standard form, and I'm stressing in its standard form, is going to be what? Is going to be yeah, it's going to be what? It's going to be zero. Okay, it's going to be zero. So please, let's take note of that, right? So let's take note of that. So having done that, so but I hope we are everyone is able to see the picture that we are building. Okay, now after we've had these elements, now we are thinking what was happening for us to form carbon dioxide and water. So this is something that I've already talked about, right? So we are having this oxygen reacting with the what? With the carbon, and this oxygen reacting with the hydrogen to produce carbon dioxide and water respectively, isn't it? So there we know to say those are the equations that we are going to play around with. So we are going to play with the equation. Now we know that this is formation, right? Carbon and oxygen forming carbon dioxide. That's standard enthalpy change of formation. Then hydrogen with oxygen forming water. That's a standard enthalpy change of formation, right? So we know the equations that we are going to use, isn't it? Now, however, from our equation, okay, so let's just leave it here. So everything that's been written here, we've discussed it using that diagram. Okay, so so here you see where we had that enthalpy change of formation for methane, but we had to reverse it. Okay, because in this case we are breaking down the methane into the elements so that we can see what really was occurring. This makes sense, right? So please, if it doesn't make sense, let me know. Okay? Yeah. Oh yeah. So we had to reverse the that equation, right? So that's why now the enthalpy change is now a positive, right? Positive 75 kilojoules. Then for oxygen, since it's an element in its standard state, so the enthalpy change of formation was zero, isn't it? Then we now go to the formation of carbon dioxide from carbon. There we have it, right? Now, when we go for the reaction, for the formation reaction for water, you see that this, remember, standard formation is always going to be for 1 mole. But look at our equation here. Look at that equation there on top, right? The one for methane, the one that we are looking at. It's got 2 moles of what? 2 moles of water. So meaning that the enthalpy, the enthalpy for what? The enthalpy for this reaction, we're going to multiply it throughout by 2, because we know that the enthalpy is going to be times 2, because it's 2 moles of water which were actually produced. Okay, so meaning we have to multiply the what? The enthalpy change of water by 2. So having said this, is everyone clear and comfortable with what we've discussed? Okay, so now, okay, so having done this and everyone is comfortable. Yes, 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 you can ask, you can ask. Hello, you can ask. Go ahead, I can hear you, you can ask. Okay, I think we may have lost the network there. Okay, okay, so please feel free to ask when you get back online, huh? Okay, so basically this is what we've been looking at, right? So now we've looked at those steps and everything. So we're just going to use this same diagram just to be able to explain a number of concepts, and then this should, then we'll just look at other examples with regards to Hess's law. Okay, so what do we have here? So you, when you look at that diagram, it's just basically showing us everything that we've done, right? Like everything that we've discussed, how we broke the, how we broke the reactants. So the reactants were taken apart and converted to elements, and which were then used to what? Which were then used to form the products, right? So this is a very exothermic reaction because very little energy is required to convert the reactants to the respective what elements, but a great deal of energy is released when these elements form the product. This is why this reaction is so useful for producing heat to warm homes and offices. Now let's now look at how they found the enthalpy for this reaction. So basically, you are looking at how many equations did we use? We used 4. The enthalpy changes of standard enthalpy changes of formation. So the first one was what? The first one was we use the standard enthalpy change for methane, but look at, there is a negative there. Why is there a negative? Because we didn't, we got the standard enthalpy change for formation, but we reversed the equation. That makes sense, right? We reversed the equation. So because we reversed the equation, and so instead of forming products, we wanted to form the reactants, right? So because of what we had done, what then we are going to have is that we are going to reverse the what? The value. So this was negative 75 kilojoules. You've seen that negative, right? Making it positive 75 kilojoules. So before I can proceed to the other things, is everyone comfortable with this?
No.
Okay. So, which part exactly aren't you comfortable with?
Step one there for enthalpy of, I don't know, the one that you're from saying.
Okay. Okay. So,
The 75 one.
okay. So, okay. So, you remember how, like, from what we discussed, to say what we are trying to form is carbon dioxide and water from the combustion of methane. Now, how can we arrive at carbon dioxide and water? We know that these compounds have come from what? Have come from the carbon and the hydrogen in methane, which were just acted on by the oxygen, isn't it? So now, because they were acted upon by the oxygen, so what we are going to do in our analysis is that we know that uh, carbon carbon and hydrogen are going to form what? Are going to form methane. Now, if we say carbon plus hydrogen form methane, then that's the enthalpy of formation, right? But because what we are trying to get in this process, remember we are going towards the right, huh? What we are trying to achieve in this process is for us to arrive at our product. So one way we can arrive at our product is by breaking apart the reactants to get the elements which are reacting. And so how do we do that? We do that by breaking apart the what? The methane. Now, how do we break apart the methane? It's going to be the opposite of the enthalpy of formation. Because you remember from when we were looking at there's one topic where we're looking at where we said, yeah, I think the same thermochemistry, where we say that uh, the amount of energy that is used to form a bond is the same amount of energy that will be required to break the bond, isn't it? So now, because we know the enthalpy of what? The enthalpy of formation for methane, which was negative 75. Therefore, to break this methane into its constituent elements is simply going to be the what? That same negative 75. That, remember, the sign is just showing you that the energy is being released. Okay, what's important is the magnitude. So it means that if we get 75 kilojoules and we plug it into, and we heat the methane, we are going to break it down into the constituent what? Elements. Therefore, because now we are no longer looking at the formation, but we're looking at the breaking, and so we are reversing the equation. That's why we have to put a negative, or rather that's why we have to since we have reversed a reaction, therefore the magnitude of the enthalpy change remains the same, but it's the sign that changes. Does that you're now comfortable with it?
Like sir, on the thing, on the diagram there it's showing 75, and then on the equation it's showing negative negative. Also, like on the equation it was direct, like they had put the two negatives aside because negative and negative is positive.
You mean which diagram? You mean the one that I'm now showing?
Yes, that's
Oh
it.
yeah, yeah, exactly, exactly. Because the enthalpy of formation here, that's why I was showing you these equations. Look at the second equation. You've seen it's negative 75, huh? Have you seen it?
Yes.
Yeah. So now when we reverse this equation, because now we are breaking down this methane into carbon and hydrogen, so we have to reverse and change the sign of what? The sign of that. So it's just negative 75. So you are multiplying it by negative, right? So you are getting positive. And the notes are even saying there, right? That we change the sign, but the magnitude remains the same. So you're now comfortable with that?
Yes.
Okay. So now, having discussed that, well, yeah, so now for oxygen, now the other equation we used, of course, enthalpy change of formation. Oxygen is in its standard form, so it's the formation, the enthalpy of formation is zero there, right? We are all comfortable with that. Where else? Now we know that from the carbon which we had produced to form carbon dioxide, the enthalpy. So here we're just using the enthalpy change of formation for carbon directly, right? Because we're not reversing anything. Perfect. We are okay. Now, when we come to the enthalpy change of formation of water, here we've multiplied it by 2. Why have we multiplied by 2? Because know that the enthalpy change of formation only is for what? For one more of a substance. But remember the equation that we are dealing with, the question, remember the question is the one on top. The question is for us to calculate the standard enthalpy change for the reaction on top, right? The combustion of methane. Now see, it's two moles of water that are being formed. So since we know that the standard enthalpy of formation is only for one mole, so we multiply it by two because we've got two moles. Is everyone comfortable with that? Okay, great. Yeah, so that's basically how then you just plug in the values and you get your answer, right? Now, this was the long method, and the reason why I wanted us to do the long method is so that you get to appreciate the short method, but more important is once you understand what's happening using the short method, you are less likely to make mistakes because you know exactly what's happening, and you are not just getting a formula and just using it, right? Because when you're just doing that, it's more or less easier to make mistakes like that, right? Because you're just plugging in values, right? So okay, excuse me. Yeah. So you want to do that, right? So you'd want to do that. Now, let's examine carefully. Okay, anyway, now let's now look at what everything that we've discussed, right? So let me show you the notes for those who may want to be following me. Okay, so just there we have cut the notes, right? So now what have we done in this? First of all, what we are looking at is the reactants were broken down into the elements in their standard states. Now that's why we didn't break down oxygen, because oxygen was already an element in its standard state, right? At least it was in its standard state. Now this process involved reversing the formation reactions and thus switching the signs of the enthalpies of formation. So what is this telling us is that what we are basically doing is that the enthalpies of formation for the reactants, we were reversing them, isn't it? Then the products were then constructed from these elements. This involved formation reactions and that's enthalpies of formation. So what we've done basically is that the enthalpy change of a given reaction can be calculated by subtracting the enthalpies of formation of the reactants from the enthalpies of formation of the products. So remember to multiply the enthalpies of formation by integers as required by the balanced equation. So I hope we've gotten that right. So what's that basically saying is from everything that we've done, it's the same as saying we get the sum of the enthalpy change of formation of the product, and we are multiplying dependent on what? Dependent on the balanced equation, right? Because you saw for the water there, we had to multiply by 2 because the balanced equation has two moles of water, right? So you get the enthalpy of formation for the product and then subtract the what? The enthalpy of formation for the reactant. Because why is this? Because you will realize that from what we calculated, we didn't change the signs for the enthalpy of formation of the product, right? But for the reactants, we were changing their signs. So that's why that negative in that formula is there to cater for the what? To cater for the reversal of the enthalpy of formation for the reactants, so as to produce the elements which are going to produce the products that we want to use in our reaction. Okay, have we gotten
So,
that?
sir,
Yes.
so what you're trying to say that when we are using this formula, there's no need of us changing the sign for the if anything for reversing is required.
Okay. Okay. Yeah. So yeah, exactly. You may remember how we were how anyway, but you look at how we do the examples. But you may remember how we are doing the cell potentials, right? Whether you can either choose to change the value, or rather to change the sign of the cell potential and then just add them, or you could just put a negative and just plug in the reduction standard potential, isn't it? Yeah, but anyway, don't worry, we'll be able to look at an example, but that's a good question. So we know the symbol delta sigma means sum of the terms. Then NP is simply saying number of moles. for the products or the reactants. So NP, of course, for the number of moles for the product, NR, number of moles for the reactants, right? So elements in their standard states are not included in enthalpy calculations. So you don't include them because they are going to be zero. So why include a zero? Okay, so that's important, right? So we have in effect defined the enthalpy of formation of an element in its standard state as zero. Since we have chosen this as our reference point for calculating enthalpy changes in reactions. So that's basically that, right? So let's now look at, before we look at our example, let's just look at this problem solving strategy. And then after we've done that, then we'll be able to answer these questions. So the first example that we'll look at, we are going to use the long method, and then for the examples that will follow, we are just going to use the short method, since now we are comfortable with the short method, right? But I love the long method because it's good for understanding, right? Okay, so the problem solving strategy. So enthalpy calculation. So when a reaction is reversed, the magnitude of the enthalpy change remains the same, but its sign changes. So its sign changes. Huh? When the balanced equation for a reaction is multiplied by an integer, the value of the enthalpy change for that reaction must be multiplied by the same integer, right? So that's what we've been doing. Then the change in enthalpy for a given reaction can be calculated from the enthalpies of formation of the reactants and products. So that's what we've discussed. Elements in their standard states are not included in the calculations for the enthalpy change of a reaction because the standard enthalpy change for an element in its zero state is what? Is zero. So that's an important point there, right? So having done this, we are now ready to answer the questions. So again, I'm going to ask, is everyone comfortable with what we've discussed so far before we can start answering questions?
Yes.
Okay. Okay, that's good. So our question, okay, going to show in a short moment. Okay, yeah, so that's our question. So that's our question, right? So next question. So using the standard enthalpies of formation listed in table 8.2, calculate the standard enthalpy change for the overall reaction that occurs when ammonia is burnt in air to form nitrogen dioxide and water. This is the first step in the manufacture of nitric acid. So we have that equation, and we have to determine the standard enthalpy change for the overall reaction. So first of all, you want the same procedure, right? What's happening here? You look at the elements. What's happening? You see that basically the products which we are having, it's just ammonia being separated, the elements being separated into nitrogen and oxygen, then oxygen acting on them, okay, to produce nitric dioxide, to produce nitrogen dioxide and to produce water, right? Of course, take note of those moles, because they are going to come in handy. They are going to come in handy. So before we can do this, let's just appreciate this diagram. I feel it's going to be very helpful. So just ignore those equations you're seeing on top. Let's just focus on that. So you see basically what I've been saying. So we get the ammonia, we break it into its elements like we've been doing. So what are we basically doing? We are reversing the enthalpy, the standard enthalpy change of formation of ammonia, right? So we are reversing it. That's how we're able to get back the elements from the compound, isn't it? Then once we've got that ammonia and hydrogen, then the oxygen now that's burning, it's now the one that's going to oxidize the nitrogen and the hydrogen to form nitrogen dioxide and to form water. So that's something that's very, very important, and so you would want to take note of that, right? Great. Where are we now? So that's something that you want to take note of. So now let's now go through this process together. Okay, so the first step, that's something that I've already explained. So you are basically just breaking down ammonia into its elements, right? So now we know that the standard reaction, so the standard reaction, okay, so the standard reaction for the formation of okay, great. Yeah, so there they are giving us okay, so we've gotten the value for the standard of formation of ammonia. Now, one thing you will realize that the first step is to decompose four moles of ammonia into nitrogen and what? And hydrogen. So the preceding reaction, so that reaction that's on top there is 4 times the reverse, the formation reaction for ammonia. Remember, when you are forming something, you always ensure that the product is what? Is 1 mole. So it means that you can use half, you can use 3/2, you can use 1/2, you can use 5/2, you can use these things, because your aim is to ensure that your product has got 1 more, isn't it? So that's why you've seen that half in front of the nitrogen gas, and that 3/2 in front of the what? Of the hydrogen, so that you have the product have being 1 more. Now when you relate it to the amount of moles of ammonia that we are having, we've got 4 moles, right? So now think of it. So this is the energy which is going to be produced, that negative, oh sorry, that 46 kilojoules per mole. So that's that. So that negative is just showing that it's going to be released, right? So that is the energy. So it means that for you to break that ammonia into its elements, you need 46 kilojoules, right? Now the question is, in our question, we've got how many moles of ammonia? 4 moles of ammonia. So therefore, how much energy do you need for you to be able to break down the 4 moles of ammonia? You need what? 4 times the energy. That makes sense, right? Does that make sense? Hello, people, tell me if it's making sense, so that I know that we are moving at the same pace. Yes? Are we understanding? Okay. So are we understanding?
Yes, sir.
Okay. Okay. So people be responding, because one thing that I'm trying to avoid is where we finish the question, then someone comes up and says, I don't understand from the beginning. That becomes very hard for me to know exactly where the person didn't understand. And then it also consumes more time, because it's easier if you don't understand here, I explain, and then we move on together, than when we finished and then I start to re-explain everything. Okay, yeah. So since everyone has understood that, so that's why we are, what's this? That's why we are multiplying by 4. But remember, this is now what? This is now positive. Why is it positive? Because remember, we are trying to get the elements from the compound, right? So it's like we are reversing the enthalpy, the equation for the enthalpy of formation. Okay, I think someone is trying to join. Let me check. Okay, okay. Yeah. So that's something that you would want to do, right? So that's about that. So let's see. Yeah, so since we've understood that part, let's now go to the second part. Now what do we have? We've got oxygen again. Oxygen is in its standard state as an element, so we know that the enthalpy of the enthalpy change for it is what? Is going to be 0, isn't it? Now this is what the money now really is, huh? Now we've got nitrogen, and we've got hydrogen, and these, we know that from these, that's where we're having the nitrogen dioxide, and this is where we are having the uh, the water being produced from the hydrogen, isn't it? So remember, check the equation. So there you're just basically looking at the enthalpy changes of formation, and then you're not going to do anything to them. Like, you're not going to reverse them, right? You're not going to reverse them because that's exactly what you are looking for, isn't it? So that's exactly what you are looking for. But then you are only going to assess and say how many moles of nitric dioxide were being formed. And it's how many? There are four, right? Four moles. So what do? It means that you multiply the enthalpy change of formation of nitric dioxide by 4. Okay, so that's something important to take note of. Then the other thing, now we're now talking about the synthesis or the formation of water, right? Of course, it's going to come from hydrogen. And again, you've seen those halves, huh? So we are using half oxygen. Why we are doing that, remember, is to ensure that our product is one more. Remember, you only do this in thermochemistry. You do this in stoichiometry. Oh my goodness. You anyway, you don't do that, right? So yeah, so that's about it, right? So yeah, so now how many moles of water are being formed? 6 moles of water. So you multiply that, the 6 times what? Times the enthalpy change of formation of water. And so you're getting that value there. So again, like we did for the earlier part, you are then going to what? You are then going to summarize everything that we've done. So summarizing what we've done, that's basically what, but anyway, we've discussed everything, right? So then now we are just going to play around with the values and then see what we can get, right? So now there was someone that asked to say, is it that we don't have to change the signs and everything? So this is why your question is going to be answered. But yeah, you just maintain the signs as they are. So for the first part, we are going to answer it using the long method, and then we are going to use the short method, right? For us to just be able to understand these things. So for us to be able to understand these things, right? So that's what we are going to do, isn't it? So now here you've got all the enthalpy changes of the equation, and what you're going to do, then you're just checking, did I reverse that? Yes, we reversed the standard enthalpy formation for ammonia. Yeah, we reversed, and because we had 4 moles of ammonia, so we multiply that by 4. Then, of course, for oxygen, if you want, you don't include it, yeah, but there you can include it. But remember that for the shorthand, we don't include it. Huh? Then the next thing that came now, so we are done away with the reactants. Now talking about the products now. So you see, we are not adding any negatives there. We are just multiplying as according to the number of moles which you are having. So let me just try to check. Maybe someone is trying to join. Okay. Yeah. So basically, that's what we are looking at, right? Yeah, so that's what we are looking at. Okay, what have we done? What have we done? Okay, great. Yeah, so that's basically that. So you see, you just plug in your values there, and you get your answer. So now, yeah, so that's basically how you do. Now, using the short method, you look at the products. What were your products? Nitrogen what? Nitrogen dioxide. And how many moles did you have? 4 moles. So you see, you are just multiplying those 4 moles times the enthalpy change of formation. Then how many moles of water did you have? You had 6 moles. You're just multiplying by the what? By the enthalpy change of formation of water. Then you now look at for the minus. Now you see the minus there? The minus, right? Okay, that now we are now talking about reactants now. Huh? So we are done talking about products. Then for that, how many moles? How many moles of yeah? So how many moles of our reactant was ammonia, right? So our reactant was ammonia. So how many moles of ammonia did we have? We had 4 moles, right? And the enthalpy change of formation was negative 46. So you see, we've maintained the same negative 46 because that's where the negative is coming from. Because once we apply that negative, it's going to become a positive, which is true because we reversed the what? We reversed the equation, isn't it? And so you get your value. So you see that we could actually have answered this question in a split second, but there is a reason why the long method is there, and I feel it really enriches your thermochemistry knowledge. Yeah? It really enriches your thermochemistry knowledge. So we're only remaining about maybe 3 or 4 questions. Then we should be done with this topic and we should start chemical kinetics. Huh? So let's look at our next question. Okay, I think in 6 minutes we can be able to do this. Yeah, since we've already understood, so I think in 6 minutes we can be able. Okay, let's just do that. So in 6 minutes we can be able to appreciate this question. So using the enthalpies of formation, calculate the standard change in enthalpy for the thermite reaction. So this thermite reaction is one of the most energetic chemical reactions known. Huh? Very powerful. So much that it's also been used in welding massive steel objects such as ships' propellers. So very powerful equation. Huh? Okay, now here's where the money is. Huh? So using enthalpies of formation, calculate the standard change in enthalpy for the thermite reaction. So there we have our reaction. This reaction occurs when a mixture of powdered aluminium and iron 3 oxide is ignited with a magnesium fuse. So first of all, what do we know about this equation? So first of all, you want to focus on your what? You want to focus on your reactants, and then you can go to the products. So for the for the for the reactants, what's the enthalpy change of formation for iron? That's what? That's iron 3 oxide. Huh? So for iron 3 oxide, what is the what's this? Yeah. So what is the enthalpy change of formation? You've got that. That's negative what? 826, right? So let's just see how we can write this so that we can have some hands-on work being done. Okay, so that's that, right? Yeah. So uh yeah, so that's what we are having. So then for this particular equation we are having so this is 2 moles aluminium, it's a solid, and then plus iron 3 oxide, right? Okay, so that's what? That's solid. Then you are forming what? You are forming aluminium oxide, which is solid, huh? And plus 2 moles of iron, not iron. So for now, for this one, we're going to use the quick method, right? Since we've gotten a hold of the long method, and so we are going to understand what's happening here. So this is aluminium. Okay, so now here, what you're going, of course, they always give you the enthalpies of formation. So we know that the enthalpy of formation for iron, for iron, for iron 3 oxide, we know that for this one, the enthalpy change of formation, the standard enthalpy change of formation for iron 3 oxide, it's negative 826 kilojoule per mole. Okay, then for the aluminium oxide, so I'm just using those to my dashes to say enthalpy, standard enthalpy change of formation, so that we can just save on time. So aluminium oxide, so it's going to be negative 1676 kilojoule per mole. Then we know that for aluminium and of uh, for ion, and remember, include the state symbols, because these things are state symbol specific, right? Because it's standard, standard, so you always want to use standard. So there is solid, and there is solid. We know that for the elements it's what? It's 0, isn't it? So then what you are going to do then is, okay, let's just do that just to create more space. So then what then you're going to do is, we just use our equation. Enthalpy change of a reaction is going to be the sum of the moles of the products multiplied by the enthalpy change of formation for the product. Okay, for the products, then minus the sum number of moles of the reactants, enthalpy change of formation for the reactants, right? Minus reactants, isn't it? So then what you're just basically going to do is just plug in values. So what do we know? And the good part about this is that those things, let me just try to check. Maybe someone wants to be let in. Let me just try to check if someone wants to be let in, so that no one happens to miss due to circumstances. Okay, okay, we are okay, we're okay. So, okay, yeah, okay, so there we have it, right? So, and we see that from those which are having the enthalpy changes of formation, they are all having one moles. So we are not multiplying anything here, right? So what you're doing, just the products. So which one is the product? Which one is the product? The product, you're only having what? What are we having for the product? The product is aluminium oxide, isn't it? So it is 676 kilojoule per mole. Then you've seen that negative, then we just write the exact thing. We don't swap it. The negative sign does it for us. So that's now we're now writing for the reactant, right? Since for the others, aluminium and iron were negatives. So when you get, so that becomes a positive, isn't it? So in essence, you are having, so in essence, you are having negative 850 kilojoules. So you see that's a lot of heat. Kilojoules. Okay, so that's what we are getting, right? So okay, of course, sorry, yeah, so if you want for this point, yeah, so that's really of value, right? If you want, I don't know why, but Zumda was not putting the moles, but since we are talking about enthalpy of formation per moles, those per moles really have to come out, I would say, since these things is per mole, isn't it? But maybe you want to specify or not, but Zumda didn't specify. So that's how you would go about these questions, right? So you see the key so you see this is a a highly exothermic reaction. So but the key thing is, you see, it's just about understanding the concepts. That's why you see, using the long method, then using the easy method or the shortcut, you've seen that the short method is making more sense, and it has seemed relatively easier, right? Because you've understood the concepts behind this. So that's really what's important. So are there any questions?